In this video, we're going to be taking a look at a fairly complex energy problem that involves elastic potential energy, gravitational potential energy, kinetic energy, and work. And what we're looking at is a block that is compressed against a spring, is pushed up a ramp, and we're going to see if it's moving at the top, and if so, what's the velocity at the end at the top of the ramp. And then we have a couple values to work with. We have the coefficient of kinetic friction, which is 0.2. And then we have some values that are associated with our spring. Okay, so our main idea is that if we use the conservation of energy, all of the initial energy plus or minus the work done on the object equals the final energy. So if it is a situation that does not involve any energy entering or leaving the system, then all of our initial energy is going to equal our final energy. Now, if you're looking at a problem like this and it's introducing a mu value, a coefficient of kinetic friction, we can safely say that friction is going to do some work in the box, and it is going to be a negative value because it's taking energy away from the object itself and then creating something like thermal energy. All right, so let's go ahead and expand our setup. Our setup is going to look something like this. All right, so what I did there is I involved the three main types of energy: elastic potential energy, gravitational potential energy, and kinetic energy. And I have initial values for all of them in the beginning at this starting position when it's compressed against the spring. And then we have all of those same things for the final position, which is at the top of the ramp right over here. So we're going to ask ourselves some simple questions to see if there are those types of energies. So in the very beginning, when it's compressed against a spring, is something stretched or compressed? The answer is definitely yes. Does it have some height off the ground? It doesn't seem so. It's going to be at a height of 0. And is it moving at the beginning? Not while it's compressed against the spring. So we just have elastic potential energy in the beginning. And I said minus W because we have some negative work done by friction. On the other end is the spring pressed or compressed or stretched at the very end. It's not anymore. Is there some height off the ground at the top of the ramp? There definitely is. And is there some kinetic energy? We're trying to answer that question, so we're not quite sure. So we're definitely going to leave that KF for the final kinetic energy. So what you do is you just keep on expanding out from our most simple form to a more and more detailed complex form. So let's go ahead and expand it out into the formulas. And it's going to look like this for elastic potential energy. It's 1/2 kx squared, 1/2 times the spring constant of 250 times the x value, which is how much the spring is compressed or stretched. So we have 1/2 kx squared for that one. And then we have minus the work. So this is going to take a little bit more of a side calculation. So work is going to be the force times the distance. And we do have the distance of 10 meters because the box is going up this ramp where the diagonal distance is 10 meters. But we don't know the force of friction quite yet. So we're going to want to use the force of friction equals mu times normal force. So we know our mu is 0.2 and we don't know our normal force quite yet. So what we want to do is we want to take a look at our box, and just like we normally do with things on an incline, we have the mg, the force of gravity, straight down. We have a perpendicular component that goes into the ramp, and we have a parallel component. Now I'm only concerned with finding this component. We'll call this FGY. And we're only concerned with that component because FGY is the exact equal and opposite value to our normal force, which is perpendicular pushing up from the ramp. Okay, so since we know Fn is equal to Fgy, once we solve for this part of the triangle, that is going to give us our Fn. So this is the adjacent side to our 30-degree angle that got translated from here to here. So the cosine of 30 degrees equals Fgy divided by Fg, and Fg is mg, mass of 2 times 9.8. So we're going to multiply both sides by 2 times 9.8, which is 19.6, which is basically cross multiplying that over. And then our Fgy comes out to 16.97 newtons. So what we're going to do is we are going to plug in the value for the force of friction, and we are going to substitute this in for 16.97 times 0.2. Okay, so we're going to take our mu, which is 0.2, times the normal force we just got, and that's going to give us our force of friction. And then we're going to take our force of friction times our distance, and that's going to give us our work. So let me go ahead and condense this a little bit. 1/2 times 250 times 1.2 squared is going to be 180 joules minus the work done by friction. So 16.97 times 0.2 times 10, which is 33.94 joules. Okay, now that's just the left side so far. That's all of our initial energy minus the work done by friction. And that equals these two on this side, our UGF plus our KF. Now we actually have all of our values for this. It's basically mg with our final H value. We know our mass is 2 kilograms. G is always 9.8. And you want to be careful because our H value is this vertical distance over here. And this diagonal distance is 10. And I can tell right now it's a 30, 60, 90 triangle. Here's the 30. This is 90. So this would be 60. So the one that's opposite of the 30 is going to be half of this 10 meters. If you wanted to set it up, it would look something like this. It would just be sine of 30 equals that vertical distance divided by 10. And then you would multiply both sides by 10, and then you would get that vertical distance. So then y would be 5 meters. So for our MGHF, we were going to do 2 kilograms times 9.8 times 5 meters. And then plus 1/2 mv squared. All right, now we have everything we need. This entire side over here is going to be 146.06 joules. 2 times 9.8 times 5 is going to be 98 joules. So let's go ahead and subtract that from both sides. And then we have 48.06 joules, which equals 1/2 mv squared. And we know our mass is going to be 2 kilograms, so we can go ahead and put that 2 there. And then the 1/2 times 2 is 1 anyway, so we don't really care about that too much. It's not going to change our answer mathematically. So then we can go ahead and then square root both sides. And that's going to give us our final velocity, which comes out to 6.93 meters per second. Okay, so to recap the problem, what you want to do is you want to start out simple. You don't necessarily need to draw this, but you definitely want to know this idea that the initial energy is going to equal the final energy as long as there isn't any energy added or subtracted to the system. You want to take a look at all your types of energy initially at your starting position, and then all of your energies after that at your final position, and ask yourself simple questions such as, is something stretched or compressed? Is something off the ground? Does it have height? And is it moving? If the answer is yes, then leave that type of energy and expand it out into its formula, which may be 1 half kx squared, mgh, or 1 half mv squared. And then after you expand it into that formula form, you plug in as many numbers as you can. You might have to do a little side work, such as this over here, and find the work done. But after that, you should have all of your values besides your unknown. Do a little bit of algebra, and that will lead you to your final solution, which it did for us, which is our final velocity of 6.93 meters per second. I hope that was helpful to you in setting up and solving an energy problem. Thanks for watching and listening.